All right, so question 8 asks, when trans 1-iodo-methyl cyclohexane, let's start by drawing that out, is heated in methanol, the product mixture is blank. So first thing we're going to do is we're going to go down our flow chart. We've got a good leaving group and a weak nucleophile. So we're thinking SN1. And so now we're going to go the SN1 route. And the steps towards SN1 is the first thing is going to happen is the leaving group's going to leave. So the iodine is going to leave. And that's going to give us a carbocation. We're going to keep our eye out for rearrangement, but there is no rearrangement. We've got secondaries next door, just like we have our secondary carbocation now. And then the next step that's going to happen is we're going to have a nucleophilic attack. So our nucleophile in this case is our weak nucleophile, our methanol. And so then what makes methanol a nucleophile is the fact that it has these lone pairs on the oxygen. So a nucleophile wants nucleuses, which in this case we're referring to nucleus as a positive charge. Electrophile wants electrons, so it wants a negative charge. But in this case we have a nucleophile, so it wants this positive charge here. And so we're going to go ahead and show our arrow attacking at that location. And so now we're going to add the whole thing, including the hydrogen. And that's going to put 3 bonds on the oxygen, which is going to make it positive. So now that gives us the hint that we need to deprotonate this. We don't want that positivity going on there. So since it didn't tell you that you only have 1 mole of methanol, we're going to use that same methanol again, which is a nucleophile, wants something positively charged. Hydrogens are positively charged, and so that's what we're going to use to deprotonate. So here we're going to go ahead and grab onto that hydrogen, which is going to leave its electrons behind, and we're going to get our product, which looks like this. And then we're going to have that methanol with the new hydrogen added onto there, which leaves that positively charged. Okay, so now something I didn't include here in this last part is the fact that we're going to get a racemic mixture out of this. We're going to have that little squiggly line, although we can't have that squiggly line because this isn't a chiral carbon, but I'm going to keep that there just so that I can explain something to you here when we're looking at our answers. So let me just go ahead and knock this out. So we've got our products, I should say. And so let's just start eliminating stuff right away. We don't have a meso compound because there's no symmetry. We've got a methyl in one case, we've got an ether in the other. They are not alcohols because we got ethers. So we can cross these guys out. And then a single chiral center, we actually have no chirality. That's because if we look here, we've got a methyl group coming off, which is one thing attached. We've got a hydrogen, that's 2 separate things, but we don't have 4 separate things because you got 1, 2, 3 carbons to get to that ether, and then 1, 2, 3 carbons to get to the other ether. And so essentially they're the same attachment. And so we don't have any chiral centers actually. So we can cross that one out. And then I mentioned that we actually don't get a racemic mixture, and that's because there's no chirality there. And so that leaves us with just this final answer of a mixture of diastereomeric ethers. And so this is where we need to explain a little bit, because what does that mean that we're having a mixture of diastereomeric ethers? And so when we have an SN1 reaction, we get racemic mixtures. And so a racemic product is going to be 50-50 resultant of the opposite configuration. So you can imagine 50% of R and 50% of S. And so the way that it relates to this problem is the fact that we're going to end up getting 50% of a compound going, of that ether going towards you, and 50% of the ether going away from you. And so when we draw that out, it's going to look like this. So these are my dashes. This is my wedge. And so ultimately from this reaction, we're getting two compounds, one where we have the ether going away from you, and the other where we have the ether going towards you. And so that's why we get a mixture of diastereomeric ethers, because this would be a trans and this is cis. And trans and cis are diastereomers, and so that's why the answer has a mixture of the diastereomeric ethers. So hopefully that makes sense. I know it's a little confusing because you don't have a chiral center there. And so you would think that, okay, well, since I don't have a chiral center, I'm not going to have that configuration showing. But just keep in mind, too, that we use cyclohexanes as chair conformations with E, and we call that 1,4-EE trans dimethyl cyclohexane. And so you can have a cis and trans without necessarily having any chirality involved, and so that becomes applicable in this problem.